In this class, let us continue our discussion on the defects in crystalline solids. Particularly, we are discussing about the point defects, the different vacancies, interstitials, Schottky pair, Frenkel pair and so on. We ended up in the earlier class discussing about the defect reactions and defect equations. We have started with one particular type of defect, that is oxygen deficiency, and this oxygen deficiency is caused by oxygen vacancy. And so, in that case, what would be the final equation and the reaction which is taking place. So, this is the final equation step by step. Okay. So, we have discussed this already. Let us go to another situation. Once again it is the oxygen vacancy, but not by oxygen once again it is a oxygen deficiency, but created not by oxygen vacancy, but metal interstitial, right. So, it is the same thing, either because we are talking about ratio. So, oxygen deficiency can be caused also by metal interstitial, and in that case what should be the kind of reaction, what would be the actual physical change, what is taking place in the oxide. So, this is once again a oxide lattice, and that is going to create a oxygen metal interstitial here. Now, this metal interstitial will be created, metal interstitial impact. This metal has come from there. Okay. This metal was originally there on this surface, and then it has come along with its two positive charges. So, along with the two positive charges it has come there. So, it has impact from regular lattice site. So, since the regular lattice site has been changed, so as we mentioned earlier, once the lattice site is not there or it has been eliminated, corresponding oxygen lattice site also have to be eliminated. Okay. So, that oxygen has actually gone out. So, metal has gone there and the corresponding oxygen cannot sit there just like that. So, it has also to go out, right. So, that is how you create a metal interstitial. So, that is how it has been written there, and of course, this in this case it is already a positive, because there was no charge here and metal has come along with these two positive charges. So, it is an effectively positive site has been created, and metal vacancy has been created there, a metal vacancy has been created there, and then half O2 has gone there, right, and leaving this metal electron over there. So, overall you can equate. Now, we are considering this is not a actual equation, is not an equality sign, you cannot write here, but if for equality sign we have to consider the lattice, one lattice, both lattices are involved here, both oxygen lattice and metal lattice are involved here. So, here oxygen vacancy is created, metal interstitials is created, then oxygen metal vacancy has also been created. Oh, there will be plus, sorry. There has to be a plus. Okay. Right. So, this is the reaction, and then I am going little fast because there are more or less similar things. Once somebody looks at it, I am sure it will be quite clear. So, that same thing, metal the electrons which were there is now been distributed to two metal ions. So, two of them has changed over to 1 plus and 1 plus, and that is how it is actually this electron has been released and it is a free electron. So, ultimately what we are getting is a metal interstitial, oxygen gas in the form which is going out. G in this case is a gas phase, that means that oxygen is not within the lattice, but it has gone out of the atmosphere. So, that is why this G parenthesis has always been used. So, it is in the form of a gas, a molecular gas, right, and that is why it is written, although it is one atom of oxygen, but basically we are writing to designate that it has gone out in the form of a molecule. So, a free electron has been, 2 free electrons have been generated, and this has been positive charge, effectively positive charge, a metal interstitial has been generated. The overall reaction will be like this. This is to denote what is happening physically in the lattice, and then both charge and mass balances, and finally, this is the equation one has to write for this reaction. So, this is but in both cases it is oxygen deficient. Okay. The ratio of metal to oxygen is more than 1. In an identical, this is the 2 things we have considered so far for the oxygen deficient oxide. 2 possibilities, one is the oxygen deficiency, other is oxygen vacancy or metal interstitial. Both of them give rise to the same thing, and in both these cases we are generating 2 electrons each, 2 electrons which are free. That means, if you are talking about in fact, we will see later on in other classes when we will consider the conductivity, these are the these are the charges or the charge carriers, and therefore, these electrons are actually giving rise to semiconductivity in this material. Okay. So, all non-stoichiometric oxides, because of the are related to the defect concentration or the point defect concentration, and depending on the point defect concentration or the nature of the point defect and the kind of non-stoichiometry, you are generating an electronic charge carrier, free electronic charge carrier, which is much more mobile and will give rise to a fairly large conductivity, and in fact, they are the origin of the oxide semiconductivity or semiconductivity in some of these oxides, particularly the transition metal oxides. So, oxygen deficiency can originate or can be caused either by oxygen deficiency, oxygen vacancy or metal interstitials. Both of them are point defects or the crystalline defects. In the identical manner, we can talk about metal deficiency. We have talked about oxygen deficiency, now we are talking about metal deficiency. It is more or less the same situation, just in a reverse manner. Here we are adding oxygen, earlier we have been releasing oxygen. If you remember, in both these cases we were releasing oxygen, right, we were releasing oxygen, oxygen is on the right and now oxygen is on the left. So, we are adding oxygen and oxygen goes into this lattice in the form of a metal vacancy. Or if you add oxygen, extra oxygen, corresponding metal you are not adding. So, metal vacancies are created. Again, I am not going to the details of that, you just anybody can go through it and find out the logic from this, how it has been written. So, half O2 G, once again half O2 gas is going into the lattice as a lattice oxygen. O subscript O means oxygen at the oxygen site. Okay. Oxygen is going at the oxygen site, this one, or M subscript M means metal going at the original M site. So, that is how it has been denoted. So, this is the original lattice site. And finally, once again the difference here is, in this case the metal is increasing its valency. Earlier cases when the oxygen deficiency was there, then the metal was decreasing its valency from 2 plus it was going to 1 plus. In this particular case, when the metal deficiency is there, the metal is going from 2 plus to 3 plus. okay, and consequently we are generating two holes, not electrons. They are also mobile species so far as the electrical conduction is concerned, but they are holes, deficiency of electrons, and they are also, or for all practical purposes, they have the similar characteristics as electrons, except that they have a positive charge while electron has a negative charge. So, we have a positive charge and those positive charges actually getting added to the 2 plus sites. So, one each to two different metals, and that is how you are creating two M3 plus sites, and they are variable valency, they can change any time. In fact, it is a kind of resonating valency. That means, for all the time they are not 3 plus. When the whole, because the whole is mobile, this is a mobile species, when it is getting attached to this, then it is become 3 plus, next time it will be once again 2 plus. So, the final reaction is like this, once again half O2G going to the metal vacancy, and then a lattice site of oxygen and two holes. That is what is the ultimate, and these are the different steps by which one can understand why we are writing this. And the last possibility is metal deficiency once again, but with oxygen interstitials. Of course, one has to remember oxygen interstitial is a little difficult, because compared to metal ions, oxygen ions are much larger. So, oxygen ion going into a oxide lattice in the interstitial position is difficult job. I mean, energetically is not that favorable. However, in certain cases it can still happen, and as a in principle that possibility exists. So, we will write that it is very simple, half O2G just going to the interstitial site. Okay. And finally, of course, the same thing happens here also, M2 plus is changed over to M3 plus, basically because we have created, or this situation creates two holes. So, these holes are mobile. So, that is what is happening here, and these are the reactions one can write as a consequence of those reactions taking place. And finally, this is the resultant. Once again the same thing has been repeated here. The three equations has been given in two different slides, has been combined here in a consolidated manner. So, we are creating two holes, and the final consolidation is here, either because of the metal deficient oxide can be created either by metal vacancy here or oxygen interstitials. Both of them will result in the same thing so far as the charge balance is concerned. Okay. We are basically interested in what kind of concentrations of different defects will be created as a result of this metal deficiency, and you can see in both the cases, whether it is metal vacancy created by metal vacancy or oxygen interstitials, in both the cases actually we are generating two holes. Earlier case, when it was oxygen deficient, it was 2 electrons, when it is metal deficient it is 2 holes, and that is as a rule it is true. That means, you have to remember whenever there is a metal deficient oxide, it will be a electron hole which are the mobile species, and they are actually we will see later on, it is actually they are the p type semiconductors. Okay. Now, these are some examples. I have given you some list earlier, a table, what are the different kind of oxides which can have non-stoichiometric compound or non-stoichiometry in them. There are examples of non-stoichiometric oxides and their formula. Formula is also given because this formula itself denotes which kind of defects they are having. Okay. For example, TiO2. TiO2 we have written as TiO2 minus X, and all these have been written as 2 minus X, TiO2 minus X, SnO2 minus X, CeO2, cerium oxide 2 minus X, ZrO2 2 minus X, and thorium oxide 2 minus X, all of them 2 minus X, which means the notation or the formula itself indicates that there is a oxygen vacancy. Oxygen vacancy is the predominating defect and they are oxygen deficient oxides, oxygen deficiency because of oxygen vacancy. Here these are metal vacancies. Okay. We have written these oxides in the form of Fe 1 minus XO, not O x minus 1, 1 minus x. First of all, it is not 1 minus x, it is not a oxygen deficient, it is metal deficient. Now, metal deficiency can be either by metal vacancy or oxygen interstitial. So, but in this case it has been observed or it has been found that they are all metal deficiency is because of metal vacancy. So, we have written 1 minus x, not 1 plus x on that side. 1 plus x will write, there is a mistake once again, there is, okay, I will come back. So, these are FeO, NiO, COO, all of them of that oxide, and 2 minus x, 1 minus x denotes that they are metal deficient and metal vacancy are the. So, there are two aspects, one is the metal deficiency, other is the metal vacancy. So, metal deficiency is created by metal vacancy or oxygen interstitials, but which one is correct, the formula itself tells you about that. So, next one is Zn 1 plus XO, it should be 1 plus XO. ZnO, CdO, cadmium oxide, chromium oxide, all of them is written as 2 plus x, 1 plus x, which means there is a metal interstitial. These are oxygen deficient oxides like this one, the first one, first category, they are oxygen deficient, less oxygen is there, but in this case the oxygen deficiency is because of oxygen vacancy, and in this case the same thing, oxygen deficiency is because of metal interstitials. So, they are very specific, they are specific, one has to understand which particular point defect is giving rise to what kind of non-stoichiometry, and that tells us a lot about its properties, about its behavior. So far as the conduction process is concerned, there are many other aspects one can understand from this information. And the last group is only one compound is there, UO2 plus X, UO2 plus X, which is uranium dioxide, and it has an oxygen interstitials. As I mentioned few minutes back, that oxygen interstitials, having oxygen interstitial in any oxide structure is very difficult, because metal ions are much smaller. Metal can go easily to the interstitial side, but oxygen, for oxygen going to the interstitial side is very energetically is not so favorable. So, but even then you have one example where oxygen does go into the interstitial side. Now, we are coming to, we have already seen some, reactions, how to write reactions. This is another few examples in a slightly different way. There are two possibilities, you know, one is what we call the ionic compensation, because we are talking about non-stoichiometric oxides. So, there is a the right kind of ratio is not there, okay, and both the species are charged species. So, if one of them is not there or available less quantity than the other, then there is a charge imbalance. Okay. So, in fact, to maintain that charge imbalance, to neutralize the charge imbalance, there has to be some charge compensation. Now, this we have already seen that the metal ions are getting either decreased in their valency or increased in their valency depending on the nature of the non-stoichiometry and nature of the defect. So, that always continues. So, that is what we call the electronic compensation. That means, the electronic charge has been, or the charge compensation has been taken care of by electronically. Electronically, that means, the charge on that particular site or charge on that particular metal, the valency of that metal had changed. So, that is what we call the electronic charge compensation. There is another charge compensation, what we call the ionic charge compensation. That means, the ions itself is missing or an ion has been added. The valency is not changing. The valency of the ion is not changing, whether it is metal ion or the oxygen ion, but the ion itself may be missing. So, the charge has gone out or and added together. So, the valency is not changing, but the metal or the oxygen ion may be the concentration may be changing. So, that is what we call ionic compensation, and this in some compounds, there are some of the important compounds where such things happen. One of the very important example is zirconium dioxide or stabilized zirconia. Zirconia, as you know, it has 3 different polymorphs, and to stabilize the highest polymorph, the cubic polymorph, you have to add some other divalent metal oxides like calcium oxide. Sometimes trivalent metal oxides are also added like yttrium oxide, but anyway, by adding here is what is called the allovalent substitution. That means, zirconium 4 plus has been substituted by calcium 2 plus. So, there is a charge imbalance, in the lattice, in the cationic site there is a charge imbalance. So, calcium goes to the zirconium site and there is a deficiency of 2 positive charges. This was 4 tetravalent and this is divalent. So, there is a deficiency of 2 positive charges. Now, this charge has to be balanced, then only calcium can go into the solid solution, right. Otherwise, if charge cannot be balanced, then it cannot go into the solid solution, it cannot form a solid solution. Fortunately, the charge has been balanced in this fashion. So, you remove some oxygen as a bodily, some oxygen ions are completely removed. Here there is no change of valency, because all these ions are very stable valent ions, whether it is oxygen, whether it is zirconium, whether it is calcium. So, zirconium valency change is very difficult, it is energetically not possible. Calcium is also the same thing. So, what can happen, that some of the ions are been removed from the lattice. So, that is what happens, oxygen vacancy created, oxygen goes out. Oxygen is fortunately all oxides it can happen, because oxygen is available in the atmosphere and at slightly elevated temperature all these reactions can take place. There is a gas solid reaction. So, oxygen can exchange between the solid and the environment. So, or it can go in or it can go out quite easily, because oxygen is available in the atmosphere, also oxygen, the same oxygen is also available within the metal. So, if the kinetics is true or kinetics is favorable, oxygen can interchange or exchange between the atmosphere and the solid. So, that is what happens. Here the oxygen goes out as soon as you push calcium into the zirconium lattice or zirconium dioxide lattice, some oxygen from this will go out in the form of oxygen vacancy, and that is what we call the ionic compensation. There is no change of valency here, there is absolutely no change in valency, only change, but still you have to maintain the charge balance, because you are adding only 2 plus instead of 4 plus. So, some negative ion has to go out, that is what happens, and it creates huge amount of oxygen vacancy, and that is advantageous for many properties. We will find later on that this oxygen vacancy give rise to huge amount of very easy oxygen mobility. Oxygen can diffuse through the lattice very easily, and that gives rise to what we call the ionic conductivity. Instead of electronic conductivity, we get ionic conductivity in this solid, and this is a very good ionic conductor, and there are huge amount of technological applications for that. We will see later on how ionic conductivity can be used. One can make a electrochemical cell, and it becomes an electrolyte. So, if you maintain two different oxygen partial pressures on the either side of these zirconia plates, one can get EMF, and that EMF, even one can use that EMF for power generation. Okay. So, that is a big advantage just by considering the point defects. So, the defects are actually so important in understanding the properties and then exploiting that properties for our benefit. Well, this is the next one, same thing, examples of defect reaction and equations. Here it is an electronic compensation. We have discussed it already, but just one or two examples, one additional example maybe. This is very specific oxide, not MO or anything. The specific oxide, iron oxide or ferrous oxide, FeO, Fe1 minus XO. If the formula itself indicate, we have a iron vacancy, and that is the reaction, that is the equation we can write, that is 2 Fe, that means Fe goes to the Fe side, half oxygen is added to the system, and then you have oxygen vacancy, iron vacancy, doubly charged iron vacancy, and this is a singly positive charge iron atom, iron ion, which means the Fe2 plus or Fe2 plus has changed over to Fe3 plus. Okay. So, Fe3 plus, this is what it means. This symbol means the iron has gone to the Fe side with a positive, effective positive charge. That means it has increased its valency, and that is possible because it has generated some holes. Okay. 2H means holes, and these are negative, effective negative charge, these are effective positive charge, and holes positive charge anyway. So, final equation is half O2G oxygen lattice, it goes to the oxygen lattice. We are adding oxygen from the outside and putting into the regular lattice side. Corresponding oxygen vacancy, corresponding iron we are not adding. So, iron vacancy is created, and that iron vacancy has effective negative charge, and that is being compensated by two holes, generated holes, which means these holes as such will not be there, it will be attached to a particular metal sides, and that is why this will actually happen. Okay. Either you proceed from this end and take this, or you can write this end to that, actually this is the final thing happens. So, this is the electronic compensation in case of Fe1 minus XO. This is another, together with that we like to find out what is the concentration, what is the partial pressure dependence of this concentration, and for that we consider an equilibrium constant for this defect equation. Whatever defect equation we have written, the same equation is written here, and you can define a equilibrium constant at a particular temperature, which is temperature dependent of course. So, this is the square brackets actually concentration. So, it is the concentration multiplied by this concentration and multiplied by this concentration. This concentration is H square, because their coefficient is 2, and on the left side you have a O2, and so half of that, this coefficient is half. So, it is actually partial pressure, concentration here can be converted to partial pressure because it is in the gas form. So, PO2 to the power 1 half. Okay. So, the equilibrium constant is the concentration, product of the concentrations of the products to the reactants, right. So, and the neutrality condition here is that from this equation itself you will find for each oxygen vacancy each metal vacancy or iron vacancy you are generating 2 holes. So, the concentration of holes is double than this, okay, that is what is written. The concentration of the holes is twice that of this. Remember, this is sometimes confusing, most of the times the mistake is 2 goes to the 2 sides on the other side, right. So, you have to see the 2 is on the right side. So, the concentration of holes is actually 2 times this, because for each iron vacancy 2 holes are being generated, right. Now, this concentration of holes is actually known as P. It is denoted by P, the positive. This comes from the semiconductor physics. So, this is this P ultimately, if you replace that in this equation, that this is replaced by P and this is P square anyway. So, it becomes P cube, and finally, this becomes proportional, the P proportional to the, this is of course constant at a particular temperature. So, it becomes proportional to PO2 to the power 1/6. So, that is a very important derivation and information that in this kind of oxides the concentration of the holes, okay, the concentration of the holes and also the concentration of this vacancy, okay, because this is related by this number of holes is equal to twice the number of oxygen iron vacancy. So, both the number of holes as well as the iron vacancy is proportional to PO2 to the power 1/6. So, higher is the potential, higher is the PO2, higher will be the concentration, and that can be shown here. If you plot log, make a log plot. I am sorry, this will be N again. This is P, okay. So, this is log P. Log P against log PO2, you will get a positive slope of 1/6, and as a rule, in fact, whenever there is a positive slope you will get a P type conductivity. So, this is a P type conduction, and of course, this slope may change, sometimes it is 1/6, sometimes it is 1/4, sometimes it is 1/8 and so on, but positive means it is P type, as the conductivity or the log P or the log concentration of the different defects increases as PO2 increases, which indicates that it may be a P type semiconductor. Another example, TiO2 minus X. The only difference here you will find that there is a oxygen vacancy, that earlier it was iron vacancy, here it is a oxygen vacancy, and if you go through this the similar process, this equation in fact it can be written as here once again 2 Ti oxygen, and then ultimately 2 oxygen, half of O2 gas goes out of the system, and so you create oxygen vacancy there. And once again you can, this is the final equation, is this one, okay, only on the metal oxygen sublattice. This is the regular oxygen site, this is half O2G which is going out, and as a result you are creating oxygen vacancy, and for charge compensation you have to create 2 electrons, not holes in this time. At this time it will be 2 electrons, otherwise the relationship exactly same. Instead of metal vacancy you have oxygen vacancy, and twice the number of oxygen vacancy is equal to the electron concentration, which is again not P n in this time, and you will get the concentration of electron, or in other words n is proportional to PO2 to the power minus 1/6. Okay. So, this is the reverse and the inverse of that. So, it is minus 1/6, and it is becoming electron. So, whenever there is a negative slope, so when you plot this, this should be an okay. So, log n that is the concentration of the electron as a function of PO2. So, it will be a negative slope, and negative slope means an n type conductor. So, that is also as a rule you have to remember. Generalized oxygen pressure dependence of defect concentration and oxide with anti-Frenkel defect. We are talking about a little bit generalized things. We have already considered what happens when there is a metal vacancy or oxygen vacancy, and in some cases we will get p type conductor or electronic compensation, another case ionic compensation, all those things we have discussed. Here we are taking a very generalized situation and considering that defects are getting created in a particular oxide. In a particular oxide, let us say MO once again, the defects are generated only at the oxygen sublattice, metal sublattice we are not including. So, in oxygen sublattice, two types of defects can take place or can be created. One is oxygen vacancy and oxygen interstitial, right. This is oxygen vacancy and this is oxygen interstitial. So, that is why it is called anti-Frenkel defect, if you remember from our original definition. So, whenever there is a presence of oxygen vacancy and oxygen interstitial, we call anti-Frenkel defect. Now, that is one of our assumptions for considering what we are going to do now. Oxygen concentration varies over a wide range. Well, oxygen concentration we do not know exactly what is the oxygen pressure range, but we are saying it varies over a very wide range. We do not know what exactly is that, right, but we will see when you come to the final results. Non-stoichiometries of both oxygen deficiency and oxygen excess are possible at extreme limits of oxygen pressure, low and high pressures respectively. We have seen in some cases oxygen vacancies are there, in some cases metal vacancies are there, but we have not seen any situation where oxygen vacancy and oxygen interstitials are present in the same system. Normally it is not a very usual system. In most cases you will find either oxygen interstitial is predominant, or oxygen vacancy is predominant, or metal vacancy is predominant, or metal interstitial is predominant. Two of them predominant all the time is not almost impossible. Here also we are talking about, we have considered two different defects, oxygen vacancy and oxygen interstitials, but we are saying that they are predominant in two different partial pressure ranges, same material, but at two different partial pressure ranges. Okay. One is predominant at very high partial pressures, which is possibly the oxygen interstitials, because you are trying to equilibrate the system at with very high concentration of oxygen. So, more oxygen can go into the system, whereas if you take a very low oxygen concentration, then oxygen will come out from the system, from this oxide. So, you can expect oxygen vacancy to be generated. So, basically what we are trying to see how the concentration, different defect concentration can change as a function of PO2 based on these two consideration, that there are only oxygen vacancy and oxygen interstitials, no other metal sublattice defects. Well, we have some interest why we are doing that, that will be clear in a minute. We can write following 4 equations, okay, following defect reactions and corresponding equilibrium constants may be written. What we are writing? There are different equilibrium situations, because we have talked about oxygen vacancy and oxygen interstitials, and if they are both of them are charged, oxygen interstitial will be negatively charged, effectively negatively charged, because you have 2 negative ions, oxygen ion, and deficiency of that will be 2 positive ions or positive charges. So, this is one kind of equilibrium, that means a lattice site, oxygen at oxygen site can go to an oxygen interstitial site, and once it leaves the lattice site, this becomes a vacancy. Okay. So, oxygen lattice site goes to the physically, the mass will go to the interstitial site, and consequently there will be oxygen vacancy. Okay. So, that is one kind of equilibrium we are considering, and that will give rise to a equilibrium constant of this nature. This of course is always 1. Okay. This concentration is so high in the lattice that this has to be taken as activity, or the concentration is 1. So, only the concentration of this multiplied by concentration of this will be an equilibrium constant of this particular reaction, or particular equilibrium. We can also have, of course, they may not be taking place simultaneously, but under different conditions we can also have this equation or this kind of reaction. That means, it is basically a oxygen deficient region. Okay. This is an oxygen deficient region which we have considered in case of TiO2. Okay. TiO2 is an oxygen deficient because of the oxygen vacancy, and we wrote very similar, exactly the same equation. So, whenever there is a oxygen vacancy is generated as a result of the reaction between the atmospheric oxygen and the oxygen within the solid, then we write this equation. Okay. Oxygen, again the oxygen at the oxygen site or the lattice site, and it goes out as oxygen vacancy, oxygen gas. Result of that, oxygen vacancy is created and 2 electrons get released. Now, this is the equilibrium constant for this, again concentration of this, concentration of this, concentration of this divided by concentration of that. This concentration is always 1. So, we define another equilibrium constant K1, this is Kf, this is K1. In fact, F stands for Frenkel, although it is anti-Frenkel, but actually we are talking about K stands for Frenkel, and this is K1. And then we can have, well, before that we can also consider this. Here we are considering oxygen vacancy at a very low PO2, but at a very high PO2 this oxygen from outside can go into the solid in the form of an oxygen interstitial, because we have already assumed that oxygen vacancy and oxygen interstitials are the predominant defect here. So, based on that assumption, if more oxygen gas is available outside in the atmosphere, and part of it will certainly pressurize the system inside to go into the system as oxygen interstitials, and once the oxygen interstitial goes in, then oxygen hole will be created. Okay. It will be created hole. So, here it was electron because oxygen vacancies were created, here oxygen interstitials have been created. So, holes have been created, and these are the fourth or third, in fact I have not considered that just now. This is the another equilibrium constant. Once again it is the concentration of this, it is the concentration of that multiplied or divided by concentration of this. Now, this time this concentration is no longer 1, this is the partial pressure of oxygen. So, this partial pressure of oxygen has been written here. Okay. Here the partial pressure of oxygen is of course on this side, on the numerator, here is on the denominator. Okay. And the fourth one is actually because we have created electrons, we have created holes. So, they will also maintain certain amount of balance. Okay. So, there will be a fourth equation which will say that annihilation, null means this electron and this hole may put together and annihilate each other. So, that means a zero resistance, a zero charge is getting generated, that is what has been written as null. So, this also will have a this also will have a, what happened, this cursor is not moving. Oh, okay. So, this will also be another equilibrium constant. So, there are 4 equilibrium constants for corresponding to 4 different reactions Kf, K1, Ke and K2. Okay, K1 and K2 are this, one is at a very high actually it will happen only at a very high oxygen partial pressure, K1 will have a very high low partial pressure oxygen, and this will continue to happen whenever there is electron and holes are there, and this is just a ionic compensation. Okay. This is ionic compensation, this is an electronic compensation, and then these are happening at 2 different partial pressure ranges. Well, only 3 of these 4 equations are required to arrive at solutions of all the concentrations, since the 2 representations of oxygen addition are equivalent, that is K1 into K2 equal to Kf into Ke square into Kf. Okay. No, Kf will not be there. This Kf will not be there. Okay. Okay, because you can see from here this equation K1 into K1 K2 actually PO2 is basically cancelling out, and it is the square of this is there, and the oxygen vacancy and oxygen interstitials are there, and then this and this is also there. So, you will find K1 K2 multiplication is actually Ke into multiple square of this. Okay. So, that is why this has been written like that, and the neutrality conditions may be written as these are negative terms or the negative charges, oxygen interstitial as well as electrons and negative charges. Oxygen interstitial has 2 charges and this is a 1 charge, and this is also positive charge. So, positive charge is on the one side and negative charge on the other side, that will be the neutrality condition. So, this must be maintained all the time, okay, because material is neutral, electrically neutral. So, this must be maintained. However, this generalized neutrality condition may be simplified depending on the exact range of PO2, either very low or very high or intermediate, and whether the electronic defect or the ionic defect equilibria predominates or not, that is whether Ke is greater than or Kf or Ke is greater than, it should be greater than or less than, sorry, is all that fine, whether Ke is greater than Kf or Ke is less than Kf. Okay. Depending on that, the situation may slightly change, will be clear when you go to the diagram. Based on these conditions, concentrations of all the possible defects have been calculated in 3 different ranges of PO2 for the 2 situations mentioned above. Log plots of defect concentrations against PO2 are shown for in A, diagram A, for Ke greater than Kf, and in B Kf greater than Ke. Now, this may not be very clear just now, but when you go to the diagram, okay, When we go to the diagram, it will be quite clear what exactly we mean. In this diagram, we have plotted PO2, log PO2, and then these are the different concentrations. There are different concentrations have been plotted. For example, this one is actually N, the concentration of electrons. This is very low PO2, very low PO2, and this is very high PO2. We have not mentioned exactly what is the range, but this is what, this is the concentration of N, that is the electronic concentration. This is on the concentration of P. Okay. On the right side, the highest one is the concentration of P, and this is the concentration of N, and this is here concentration of P, and on this side concentration of N. So, all these 4 different defects have been calculated as a function of P, PO2, and this is the variation. N varies, the number of holes, the number of electrons varies in this manner with a slope of minus 1/6. Okay. It is 1/6, and then it goes there, it becomes constant. At a intermediate PO2, N becomes P, and then on this side is P, and N becomes lower. So, on this side N dominates, P is very low. Other values of these are oxygen vacancies, these are oxygen interstitials. The oxygen interstitials changes from this manner and becomes very comparable to the concentration of holes on the right side, and oxygen vacancy is very low on this side and then goes like that, and it becomes comparable to the electronic concentration. But electron concentration is higher, still higher than the oxygen vacancy or oxygen interstitial. On this side it is whole concentration is higher, and there is an intermediate temperature range where N is equal to P, that means number of electrons and number of holes are same. Okay. So, this means, and these intersections, this is an intersection of actually K1. Okay. This one, no, this is Kf. Okay. Sorry, I will tell you. This intersection is Kf. This is oxygen vacancy and oxygen interstitials. That was the equilibrium constant for that. And here it is the Ke. This is Ke. Okay, where the concentration of N and P is same. The difference between this diagram and this diagram is, you can see the here the this oxygen vacancy and oxygen interstitials are same in this flat region. This is PO2 independent region. Okay. This is PO2 independent region where the compensation is ionic compensation, whereas in the here PO2 independent, there is also PO2 independent, also this is small region, but the compensation is electronic compensation, right. So, what it basically means that this is the stoichiometric crystal is written here, this is a stoichiometric crystal, this is also a stoichiometric crystal. So, in this region you have an electronic conductivity, all through in fact it has an electronic conductivity depending on which is this value. Here you can see this is Ke, Ke is less than this value, this is K1 into K2 Kf, okay. This is Kf and this is Ke. So, here Ke is much smaller than Kf, where here Kf is smaller than Ke. So, this corresponds to Ke, the electronic compensation, and this is the ionic compensation. So, the ionic compensation is less important here, electronic is important here, electronic is less important, ionic is important. Now, this of course depends on the particular solid, which particular solid, but this is a very generalized situation for any oxide, whatever oxide you take, whatever oxide you take, you will get this kind of a variation, and at very low PO2 it will be an electronic conductor, At very high PO2 it is a p type conductor, hole conductor, or it can be and there will be a intermediate region where it will be either a intrinsic conductivity, that means N equal to P means in semiconductor terminology we call it an intrinsic conductivity, or a completely ionic conductor. So, this is possible for any, this is a very generalized situation. The whole range is not applicable to all the oxides. Some of the oxide resides here, mostly stoichiometric, for example zirconia like things, which are ionic compensation is the more important thing. So, we have not given here any particular value of PO2. Okay. So, that is also variable from material to material. So, in some cases the material will behave in this manner or fall in this range, in some cases the material will fall, another material will fall in this range. So, there are materials where or oxides which are normally ionic conductors. So, they follow this kind of a situation. There are other oxides which are normally hole type conductor. So, they will be falling in this range, and there will be another category of oxides which are normally or mostly negative or electronic conductor, they will fall in this category. So, if you have a material of this nature, basically an electronic conductor, if you go on increasing the PO2, at some point you will reach this. It is not known at what partial pressure, at what high pressure or not, we may experimentally you may or may not reach, but theoretically you are supposed to go to this. Similarly, if you have a ionic conductor like this and then expose it to a very low PO2, at some point of time it will become a N type conductor, electronic conductor. The same material, if you take it to a very high PO2, very high partial pressure, maybe several atmospheres of partial pressure, then it will become a P type conductor. So, it is not that all the materials will have a permanently ionic conductor or a electronic conductor or a hole conductor. They can be changed depending on the PO2, depending on the temperature and so on, but all those things to a large extent has to be determined experimentally. So, this is the essence of this kind of a calculation and this kind of a diagram. Okay. Finally, I think there is only a couple of slides. Defect concentration, thermal effect. What we have discussed so far, the defect concentration changes with the partial pressure, because it equilibrates with the environment, and depending on its preparation condition, depending on the environmental condition, the partial pressure, the defect concentration will change, and accordingly its conductivity, its mobility, its diffusion coefficient, all of them will change, whatever is related to the defect concentration, whether it is ionic defects or electronic defects, it will certainly change, right. But there is another very important parameter which also has a great influence on the defect concentration, that is thermal effect, the temperature effect, and that is what it is written here. The generation of point defects, generation of point defect increases structural energy of a crystal, at the same time it increases the entropy, randomness of the atomic position of the system. Dominance of the entropy term, particularly at higher temperature, results in lowering of free energy of the system. So, formation of defect is a preferred phenomena, particularly at high temperature. So, it is not that defects are not allowed, defects are actually preferred, because by generating this kind of point defects, actually you change, you reduce the free energy of the system. Okay, because the entropy term increases, and by increasing the entropy term you actually reduce the free energy, and therefore defects will automatically form at high temperature. Okay. So, where depending on the temperature defects are automatically going to come, and it is a preferred thing from the thermodynamic point of view. I think that is what, since most materials are prepared at high temperature, defects are invariably present in all materials except when they are prepared with special care, extremely slow rate of cooling. If somebody wants a very pure material or not only pure, I mean defect free material, then it has to take a very special care so that the defects are not generated, but under normal circumstances defect will be generated, and they actually tend to minimize the free energy of the system, and free energy of the system minimization means it is more stable thermodynamically. Finally, this is the equation, which is a very simple Arrhenius kind of equation. Mathematically, the defect concentration is expressed as n by n. This is basically a concentration term, exponential minus delta H by 2 kT, delta H enthalpy of formation of the defect. So, for formation of each defect there is enthalpy term, and associated with each defect we have enthalpy term. So, that depends on the particular type of defect, the structure of the material in which it is getting generated, and so on. So, where n by n is the concentration of concentration of any particular defect, delta H is the heat of formation of one defect, K is the Boltzmann constant, and T is the temperature in degree Kelvin. The value of delta H is usually 1 to 10 electron volt. At a typical temperature of 1000 degree centigrade, the concentration may vary from 10 to the minus 2 to around 10 to the minus 7, depending on the value of delta H, which may vary from 1 to 8 electron volt. Well, that is all I think about our discussion on the imperfections in crystals or point defect in crystals, and as you can see, there is an enormous importance of the point defects when you try to discuss or try to understand some of the physical properties like the electrical conductivity as well as diffusion coefficient. Particularly these two properties are very critical for understanding that. You must have a good idea about the defect characteristics and how it is generated, under what conditions it can be influenced, and so on and so forth. So, with this we come to the end of this discussion, and thank you very much for your kind attention.